Alright, let's look at the homework 8, problem number 17. Alright, so we want to sketch the graph of f of x equals 3x squared over x minus 3. Alright, so let's answer the first question. Domain, right? So when you have a rational function, we have to make sure that the denominator is non-zero. Right? So if you look at the denominator, which is x minus 3, so when x equals 3, denominator becomes 0. Right? So we have to eliminate that. So all real numbers except for 3. Right? So check the answer. Right? So we got that one. Right? So let's find the x-intercept. Right? So in order to find x-intercept, we set the whole function equal to 0. So whenever we want to find the x-intercept, we basically set y equal to 0, right? But y being the whole function. So we set 3x squared over x minus 3 equal to 0, right? But when the fraction is 0, we just have to make sure that the numerator is 0. So you have a 3x squared is equal to 0. So you can see that this happens when x equals 0. Right? So x-intercept is 0. Right? So let's check the answer. Right? So we got that. So if you want the y-intercept, we set x equal to 0. Right? So we basically, put x equals 0 into that function. Right? So you have 3 times 0 squared over 0 minus 3 is, of course, it's 0. Right? So y-intercept is actually also 0. Right? Check the answer. So we got that. Alright, then we want to find x-intercept. So vertical asymptote, vertical asymptote. So a rational function will have a vertical asymptote when the numerator is non-zero and the denominator is 0. So we basically set the denominator equal to 0. Then we have by adding 3 to both sides, so we get the x equals 3. And this is the vertical asymptote. Right? So let's type it in. X equals 3 is a vertical asymptote. Alright, so we got that. Alright, horizontal asymptote. Alright, when you have a rational function, here's a trick. When you have a higher power on top, so the power on top is 2, and the power on the bottom is 1. So when you have a higher power on the numerator than the denominator, there is no horizontal asymptotes. If they have the same powers on top and bottom, then y equals the leading coefficient on top over the leading coefficient of bottom will give you the horizontal asymptote. If the bottom has a higher power, y equals 0 is the horizontal asymptote. But in this case, the top has a higher power. There is no horizontal asymptote. Alright, so let's check the answer. Alright, we got that. Alright, so we're going to look at the first derivative and then talk about the increasing, decreasing behavior of the original function. Alright, so let's do that. Alright, so we need to find the derivative. So f prime of x is equal to, alright, so I'm going to use a quotient rule, and since the 3's are just a constant multiple, so I'll just put it in front. Right, so it's a quotient rule. Right, square the denominator, so you have x minus 3 squared. Right, then derivative of the top is 2x times the denominator is quantity x minus 3 minus top is x squared times derivative of the denominator is 1. Alright, so we can simplify it as, alright, so you have a 3 from the front, and you have a 2x squared, oops, and minus x squared would be x squared, minus 2x times negative 3 would be negative 6x, and over x minus 3 squared. Alright, then we're going to pull out the x. Then we have a x minus 6 over quantity x minus 3 squared. Right? So we set this guy equal to 0, so we can see that we set the numerator equal to 0. So x equals 0 and x equals 6 are the critical numbers. Right? So let's do a number line on this guy. So I'm going to just use a number line here. Alright, and I'm going to put a tick marks on at 0 and also at 6. Alright, then we're going to look at the sign of f prime. Alright, and let's try some simple number, anything less than 0. So like x equals negative 1. Alright, and you can see that, so this is the first derivative. And denominator is always positive because it has a square there, right? Let's try negative 1. So it's 3 times negative 1 and times negative 7. So positive times negative positive. So we're going to have a positive sign here, right? So anything between 0 and 6, I'll try 1. Alright, so you have a 3 times 1's positive, 1 minus 6 negative, so it's going to be negative. Right? And try anything bigger than 6, so I'll try 7. Right? Positive times 7, positive. 7 minus 6, positive, so everyone's positive, so it's going to be positive. Alright, so you can see that the original function f is increasing on infinity to 0. Right, and decreasing on between 0 and 6, and increasing after 6. Right, so let's type it in. Alright, so it's increasing on from negative infinity to 0, and also, and we have to use a comma to separate them. And from 6 to infinity, and decreasing between 0 and 6. Right, so let's check the answer. Right, let's see. Right, second answer is not correct. Let's see. Let's double check. Let's see what's wrong here. Decreasing, or maybe I'll put square bracket, see if this is going to be correct. Oh, okay. You know what I did? Sorry, I made a mistake here. Alright, remember that here x equals 3 is not defined, so I should have put x equals 3 there. Alright, and then we have to do this separately. Alright, but in this case we know that negative sign. Alright, so this is going to be still, you can try x equals 1 and x equals 4, something like that, but it's going to turn out to be negative here and a negative there. Alright, so what we need to do is here, instead of 0 to 6, I'm going to have to actually eliminate 3, because which makes sense, right? Because 3 shouldn't be included. So 3 to 6. And how about that? All right, we got that. Sorry about that. All right, so we have that. All right, then we want to look at local max and local minimum. All right, so let's look at the number line here. All right, so we have increasing, decreasing behavior. So it's increasing turning into decreasing. So we can see that this is the top of the hill. So this is going to be a local maximum. All right. Then, so at 3 it's not defined, so we wouldn't have a local maximum minimum. But here, it's decreasing, turning into increasing. So you're going to have a local minimum there. Alright, so local max at 0, local minimum at 6. Alright, so here, let's see, local maximum at 0, local minimum at 6. Alright, let's check the answer. Alright, we got that. Alright, then we have to look at the second derivative, and then we have to discuss concavity. Alright, so let's do that. Alright, so second derivative. So we're looking at, let's see, which one should I look at? Let's look at this one. Alright, so let's take the derivative of that. So f double prime of x is equal to, alright, so in this case 3 is just a constant multiple, so I put that there. Alright, then again we use the quotient rule. Alright, square the bottom, so you're going to have x minus 3 already squared, so it's going to be to the 4th power. Alright, then derivative of the top, which is going to be 2x minus 6. So we have a 2x minus 6 times the denominator, which is x minus 3 squared. Alright, minus, right, top is x squared minus 6x times the derivative of the denominator. So put that 2 in front, keep the same inside function, subtract 1 from the power 1, and multiply by derivative inside is 1. So I'm not going to write that because it's not going to really do anything. Alright, so we have that. Then let's simplify a bit. Alright, so we have x minus 3. So I'm going to pull out the, so 3 is already there. Alright, then seems like x minus 3 is in common. So let's, so here's x minus 3 here. And there are actually 2 of them, so I'll just circle that so I know that there's another x minus 3 there. So we have that. Then let's collect the remaining terms. Alright, so we have, you have another x minus 3. So there's actually, if you pull 2 out from here, you're going to have actually another x minus 3 there. So I'm going to just go ahead and do that. So if you pull out the 2 from there, let's see, so that changed it to 6. Right, 6, right? Alright, so 2 is here. And this is same thing as 2 times x minus 3. So this 2 is also pulled out. Alright, so we have that. Alright, then what's left is going to be, so x minus 3, so it's x squared minus 6x plus 9. Alright, then minus, right here you have x squared, right, minus 6x, so it's going to be, let's see, plus 6x, right? So we have that. Alright, then divided by, alright, x minus 3 to the 4th power. Alright, so then we can cancel x minus 3 there, and one of them cancel out, so we have that. Then you have negative 6x, and you have a positive 6x. Then you have x squared and a negative x squared. Alright, so you're going to have actually 6 times 9, 54, over x minus 3 cubed. Alright, so we have to do a number line here. So in this case, only number, this is never 0, right? Because top is always 54 and the denominator can't make a whole thing equal to 0. So the only thing we have to worry about is say x equals 3, right? Because it's not, the function is not defined there. Then we look at the second derivative and then try anything less than 3. So let's try, I like 1, right? So if you plug in 1, 1 minus 3 cubed is going to be negative. 50 over negative, 54 over negative number is negative sign here, right? And if you try anything bigger than 3, so let's 4. 4 minus 3 is positive, so it's going to be positive, right? Which means that the original function is going to be concave downward here, and after that concave upward there. All right, so let's type that in. All right, concave upward on, let's see, it was actually from 3, so all right, concave upward on 3 to positive infinity. All right, and then from negative infinity to 3, it's concave down. So let's check the answer. All right, so we got that. All right, so inflection point. Let's see, only possible inflection point would be at the x equals 3, but the function is actually not defined at x equals 3, so there is no inflection points. Right, so there's no inflection points. Got that. All right, then we want to look for the correct graph. So x equals 3, it's not defined, so C is not going to be it, and the vertical asymptote, okay, so D looks promising, and B is not going to be it, so it's going to be between A and D. Right, so let's look at the increasing, decreasing behavior. Oh, actually, let's look at the concavity. Right, remember that it's concave down turning into concave up. So let's see, concave down turning into concave up. A is promising. D is concave up turning into concave down. So A is the only one that fits the description. Right, let's check the answer. All right, so we got that. All right. That's it. I hope that this was clear.